Greetings everyone and welcome to Revolution of Reality, a channel that describes the scientific revolution that could soon be precipitated by telepathy experiments. In this episode, I will discuss the painful history that should lead to physicists becoming interested in telepathy experiments, or anything else that could provide them with the evidence they desperately need to solve the current crisis in physics. The painful history I'm referring to involves the largest and most complex machine ever built, the Large Hadron Collider, or LHC. It includes a huge 27-kilometer-long circular tunnel on the border between France and Switzerland. It was built up to 175 meters below the ground to minimize impact on the environment. Here's what's in the circular tunnel. 27 kilometers of this large, complex, expensive equipment, plus 4 gigantic detectors up to 7 stories high. See how small this technician appears in comparison. Paradoxically, the purpose of these largest machines is to analyze the smallest particles, atoms. In a sense, it is zooming in on the atom to analyze its inner workings. It does this by accelerating subatomic particles, such as protons, to very high speeds, and then allowing them to smash into each other from opposite directions. The resulting energy is then analyzed by detectors, and if an unknown energy is found, that indicates that new physics has been found, usually in the form of a new particle. Particle colliders played a major role in the development of the standard model of elementary particles. This is the foundation of physics, since everything is made of particles. Even light is made of particles called photons. The standard model is the theory that physicists have put forward to explain how the universe fundamentally works. However, when it was formulated in the mid-1970s, there were still some particles that had been predicted by theory but not yet confirmed by evidence. As colliders grew bigger and more diverse, they were able to confirm these particles one by one. However, there was one particle that was so elusive it earned a nickname, the God particle. The Higgs boson was first predicted in 1964 by Peter Higgs and others, and nearly half a century later it took the largest machine ever built to find it, which took place in 2012. However, the theory of the Higgs comes with good news and bad news. The good news is that it provides a solution to the mass problem, which relates to the mass of particles. The bad news is that the mass of the Higgs itself is too light. In fact, it's about 100 quadrillion times too light when compared to the theory of the Standard Model. This was discovered in 1976, just after the Standard Model had been completed. I won't go into the complicated reasons for all of this, but suffice to say that the chances of the Higgs ending up with this ultralight mass are extremely, extremely small. Experts often compare this unlikely Higgs mass to a pencil standing on its tip. It's still standing even though there have been a lot of air currents and table vibrations pushing it around. One possibility is that every table vibration was exactly matched by an air current pushing in the opposite direction. But of course, that seems ludicrous, so instead, physicists began to look for hidden strings that kept the pencil from falling over, metaphorically speaking. And indeed, they found one, an idea called supersymmetry. It was called a beautiful theory. Some even thought it was too beautiful to be wrong. The strength and beauty of supersymmetry lies in its potential to solve a number of problems using one theory. Supersymmetry proposes that each of the particles in the Standard Model has a supersymmetry partner that has yet to be discovered. However, colliders were not powerful enough to discover these supersymmetry particles at the time, and ultimately physicists would end up waiting more than 3 decades for the LHC to put supersymmetry to the test when it started up in 2010. Supersymmetry potentially solves 2 of the Standard Model deficiencies, which are discussed in previous episodes. Firstly, the hierarchy problem, which is the one I described earlier regarding the Higgs mass, and secondly, the dark matter problem. However, The other deficiencies also need to be solved, and it is believed that they can also be solved in the same sort of way as supersymmetry, by finding new particles or new physics hidden inside the atom. So the goal of the LHC was firstly to find the Higgs boson, and secondly to find new physics, especially supersymmetry particles, in order to address the deficiencies of the Standard Model. When the LHC began gearing up for its first run in 2010, there was much excitement, especially given how much had gone into this project. The LHC was a monumental global effort, involving over 10,000 scientists and engineers, and over 100 countries. It took 25 years from the start of planning to the start of operation, and there was a decade of negotiations leading up to the go-ahead. Bearing all of that in mind, you might expect that the term nightmare scenario would refer to the scenario where the LHC makes no discoveries at all. Indeed, that would have been a nightmare scenario, but it was an unlikely scenario, since a combination of existing evidence and theory strongly indicated that the Higgs would be found. Instead, the term nightmare scenario arose from a much more realistic fear, the fear that the LHC might find the Higgs and nothing else, as laid out in this article from 2007, which states that many particle physicists say their greatest fear is that their grand new machine will spot the Higgs and nothing else. If so, particle physics could grind to halt, they say. The reason particle physics would hit a metaphoric brick wall and grind to halt is because evidence of new physics in the atom would now be out of reach for at least 3 to 4 decades, which is how long it would take to get a bigger collider up and running, if funding is granted, which seems unlikely. In the meantime, you would be completely stuck without knowing where to turn next to solve the Standard Model's problems. It would leave physicists even more thoroughly stymied than before, said Jonathan Ellis, one of the leading physicists on the project. This would be the real 5-star disaster. I'm terrified, said Nobel laureate Steven Weinberg. Discovering just the Higgs would really be a crisis. However, most physicists were optimistic about the discovery of supersymmetry particles. According to this article in 2001, nearly 30 years after its discovery, supersymmetry remains the prime candidate to cure all of the ills of our understanding of elementary particle behavior. More than 30,000 theoretical papers have been published on supersymmetry, and many people believe it will dominate and revolutionize fundamental physics in the century ahead. So when the LHC began its first run in 2010, it was time to find out which of these 30,000 papers was on the right track, and whose career was going to benefit. After a couple of years, the big announcement came in the mainstream media. The Higgs boson had been found. But by the end of the first run, it was the Higgs and nothing else.
My experiment published paper after paper where we glumly had to conclude that we saw no signs of new physics.
The search for new physics was not over yet, and physicists would need to wait another 6 more years for the second run to be completed. The next 2 years were spent upgrading the LHC to a higher energy capacity. However, most physicists had concluded that supersymmetry should be found at the lower energy and is highly unlikely to be found at the high energy or by a bigger collider. So at this point, the nightmare scenario was already looming large over physics, and during the shutdown, this article was published in Scientific American. The headline warns that, if supersymmetry doesn't pan out, scientists need a new way to explain the universe. Because without supersymmetry, physicists need to come up with radical new ideas to explain problems that look like this. The article referred to the mighty cathedral of theoretical physics that physicists had built up over the past half-century. This mighty cathedral was built on a foundation of supersymmetry, and its origins stretched all the way back to the early 1970s. So this cathedral was the work of a generation. If at the end of the second run nothing new showed up at the LHC, there would be no realistic path forward other than to abandon the work of a generation. The article spoke of widespread panic. Theorists are walking around in a bit of stunned silence, said Neil Turok, director of the Perimeter Institute for Theoretical Physics at the time. In March of 2015, the LHC began its second run, and this time the future of physics was on the line.
The stakes now could not be higher. This summer, the LHC began its second phase of operation with an energy almost double what we achieved in the first run. What particle physicists are all desperately hoping for are signs of new particles, micro black holes, or maybe something totally unexpected emerging from the violent collisions at the Large Hadron Collider.
But it was not to be. At the end of 2018, it was still the Higgs and nothing else. Physicists were now confronting their nightmare scenario.
At this point, we're absolutely stuck. We absolutely don't know where we're heading.
My impression is that most of my community is a little bit shell-shocked by what happened. There's certainly no consensus in the community to move forward. So my response is, I think that maybe we should just go back to the drawing board and start to challenge some of the assumptions and paradigms that we've been holding for the past 30 years. It feels good to me that everyone was wrong. You know, it's when we're wrong that we start to make progress.
My view is that this has been a kind of catastrophe. We've lost our way, said Neil Turok. Indeed, it means that the foundations of physics have not progressed for 40 years. The progress in fundamental physics, very roughly, looks like this. There was ongoing progress up until about the end of the 1970s, just after the Standard Model was formulated, and since then there has been no progress on new theories to take us beyond the Standard Model, which is deficient. If supersymmetry particles had been found, it would have turned this into a period of progress, with optimism for more progress ahead. Instead, we are now facing the prospect of many more decades of no progress. If politicians agree to fund a bigger collider, which seems unlikely at this point, then we can expect the next verdict on new physics in about 3 to 4 decades' time, but it will be a bit like stabbing in the dark. The lack of progress could drag on indefinitely, and even young physicists are aware that they might go to their graves without ever finding answers to the questions that they have grappled with throughout their lives. It's under these nightmarish circumstances that telepathy experiments could now step up to the plate and provide physicists with some very welcome direction. If validated, telepathy experiments would show that physics is on the wrong track. The universe is structured completely differently to what we have always assumed, because space and time are actually an illusion, or emergent in physics terminology. Telepathy experiments could provide a dream end to the nightmare scenario, even though it might be a bit uncomfortable at first, as will be discussed in my next video.